So in this example, we're repeating example 5 where we found the Fourier transform of the top hat function. In this example, we're going to make use of the symmetry properties of this function. The function is sketched just here, and what we can see is it has even symmetry. It has reflection symmetry about the vertical axis. So this means we can use the Fourier cosine approach, which sometimes makes the maths a little simpler. To do this, we need the relevant equation. I've copied it here from the lecture notes. The only thing we'll need to do is write this equation in terms of omega and t. In the notes, it's defined in terms of k and x. So what we can do now is we can write that f of omega, the Fourier transform of our function, is the square root of 2 divided by pi. It's the integral between 0. Now the function falls to 0 at plus tau, so we make plus tau the upper limit of the integral. Beyond that value, the function is always 0. Between 0 and tau, the function has a value 1, so we write a 1 there, and then we have a cos omega t, and then the integral is with respect to dt. You can see that this is a simple cosine integral. This gives us the square root of 2 divided by pi, and then the cosine function integrates up to sine omega t, and as a factor of omega comes out, which goes in the denominator. We can now put in the limits of our integral, so we have the square root of 2 over pi as always, and then the upper limit gives you sine omega tau, and in the bottom there's an omega. The lower limit just gives us 0 because sine of 0 is equal to 0. And finally, we just need to manipulate slightly. We can write this again. We put a factor of tau in the top and the bottom of the function, just so that it becomes a function of omega tau. And then we also need to multiply top and bottom by the square root of 2, and that will give us the form that we got before. So the multiplying by root 2 in the top gives us a 2. We put in our factor. We put in our factor of tau, and then in the bottom we've got square root of pi. We've got now another square root of 2, so we get square root of 2 pi, and then we have sine omega tau divided by omega tau, and this is the same result that we got when we used the complex exponential approach.